You mentioned a few areas when I came yesterday that were very interesting that I'd love for you to expand more upon. So perhaps you could pick up upon 2 or 3 things in your mind as the most cutting edge, the most visionary that would really grab people's attention and interest.
Okay.
So you brought up machine learning and DevOps, Kubernetes, containerization, cybersecurity. So maybe you could pick one of those or even something else that you just feel.
No, I think we can probably talk about or kind of like together think about DevOps, data, and machine learning, and kind of like how those 3 things could come together into kind of like this concept. Okay, so when you look at DevOps from a historical perspective, in the past you had developers on one side, you had operations in another, right? They participated at different stages of the life cycle of a product, and that was slow and that was full of friction, right? And that was kind of like this siloed scenario, okay? What DevOps came to bring to the table is now you have a unified life cycle ownership of your product. Now, those that are developing it and those that are managing it in a productive environment, those that are validating its quality, are all participating throughout the full life cycle of the product. Now, they own the product end to end. But there are some areas still that are siloed outside of that continuous delivery, okay? Data is one of those things. Right now, currently, the way that I see it for the most part is data science happens after the fact. You build a product, you build a system, that system stores its data in a way that is meaningful for the system. And it's delivered to the users. And then the data scientists, after that fact, go and start trying to find meaning to that data and try to coalesce data from any number of sources into features that are relevant for their machine learning prediction.
So are you talking mostly about server log files and then they...
No. I'm talking about data itself. I'm talking about when you're building a system, let's imagine a very basic use case of, I don't know, some task management product, right? You have users, and those users are in a database somewhere, and they have a name and an email, and you have tasks that have an owner and an expected completion date, right? That is data. And that data is stored in relational databases or NoSQL databases, and those schemas and those relations are built to satisfy use cases of the product. But those use cases of the product are not necessarily meaningful in terms of features required for a data scientist to feed into their machine learning models, okay? For a machine learning model to work and to predict, you have to give it a whole bunch of data, and you have to identify mathematical representations of those real-world objects or actions that you want to predict, right? So for you don't care about one user or their email address. You want to look at how you take that data and convert it into meaningful features. And when I say features, I'm talking about data science features. Okay. So I'm not talking about
the front end looks...
No. So let me give kind of like just some backing to that. In data science, and I'm gonna let Wikipedia do this better than I can. So, in data science, feature engineering is the process of using domain knowledge of the data to create features that make machine learning algorithms work. Feature engineering is fundamental to the application of machine learning and is both difficult and expensive, according to Wikipedia. So that's kind of like what a data scientist does. They write an algorithm that is fed to some machine learning framework, and they feed data to that algorithm. But the data has been manipulated. It has been manipulated into features. It has been engineered into features. What the machine learning models receive is not raw data, it's processed data that matches those features that they're using to predict. Okay?
Now which data is it pulling in from the DevOps side?
Anything. That's basically the point. You see what I'm saying? When you're building your application, right now, when you have somebody working on a specific use case, some user story, it never, it's not in the mindset of the product owner, and it's not in the mindset of the developer how that data may eventually be used to feed a machine learning model, for example. Because the whole data science happens after the fact. So what these guys are storing in their databases, the schemas, the structure, the relationships that they're building, are completely oblivious to the eventual use of their data for a data science application. Okay, why is that? Because the data science is siloed somewhere else, which is the same thing that happened with DevOps in the beginning. The developers were completely oblivious of the fact that this is going to be running an operation somewhere and how that infrastructure was deployed, what that infrastructure looked like. It was impossible for them to see that or to reproduce that. DevOps brings that together. So now they understand we got the cloud, we got our serverless functions, we got our containers. I can run the containers here, and those same containers are going to be running somewhere else. They now have visibility, and now they have that in their mindset when they're building their software. They're building it in a way that is compatible, that is friendly to the environment we will be running, because they have that visibility, because now they've joined forces between devs and ops. The same problem is happening right now with data. Everything that is architected, everything that is designed by these guys is completely oblivious to the fact that they are going to be feeding some machine learning algorithm in the future. So what they're building may not be friendly to that algorithm. So that's what happens with the current process. Data scientists have to start collecting information from multiple sources. And this is why we have ETL pipelines and ELT pipelines to extract data from a whole bunch of different locations and transform it into something that's meaningful, which introduces a whole lot of latency and makes feeding these machine learning models complicated and expensive. If you bring the data science into your delivery lifecycle, into your software lifecycle, if you get the data scientists out of their silo and into your product development and design cycles, then the data that you're storing might be directly usable by your machine learning models. Maybe we can skip the ETL altogether, because we now have in our mindset that this data is not there just to satisfy a functional feature, is there to also satisfy an eventual machine learning model that will predict something.
Okay,
See what-
the DevOps output is living closely where the machine learning algorithms can process that information rather than having to export it via ETL or just have it in a whole separate silo where there may or may not be time or resources to even do anything with it.
Yeah.
So we'll be in a specific example of a way a machine learning algorithm could help provide increased efficiencies or save money or something besides being more readily available.
Okay, I'm gonna flip that around. So basically, what I'm thinking is, you're designing a feature. You have a machine learning algorithm that is there to predict, given a certain user profile, what will be the likelihood of them using the software product once a day or once a week or once a month. Okay, so what we're trying to predict is how often will my user use this product. What I can use to identify that is something, for example, along the lines of login frequency and session time. Okay? And I write a machine learning algorithm that gets those values and predicts something. If this person or the person logs in every week and their session is 30 minutes long, then I want to predict whether that user is gonna be coming more often later on or less often later on. Or I want to predict if the users that are spending less time are more likely to close their accounts within a given time period. Okay, so that is what my machine learning model is trying to predict. And what it is using to predict that are data science features that have been engineered, mathematical representations that my machine learning model is using to predict that. So, for example, session time or number of logins or who knows what else, right? The further away your data structures are from the expected input of the machine learning model, the more complex your process is going to be, the more delayed your process is going to be to get your real-time data usable by your machine learning model. Because the guys that built that schema, the developers that built the schema that holds the data that eventually will be used for this, had no idea what the feature that the data scientist engineer was trying to accomplish looked like. So the data scientist could have said, hey, you know what? Right then and there, you have a mechanism to increase a monthly counter of logins. And that gives me my feature already. I don't have to query for each user's history, then calculate on a daily bucket how many times and how many minutes they were there. If you could just basically aggregate that when the user logs into a row in the table, then you saved me all my ETL process.
Okay, you can more efficiently handle that user, and you can also predict server loads, which time of the day, like maybe before the stock market closes, if there's higher usage, all those kinds of things.
You could predict anything, but the point is, what can be predicted is defined by your data input. Your data input needs to be something that is meaningful as a representation of something in the real world, right? Because you're trying to determine something in the real world as an output. If your data scientist is participating in the design process of your product from the start, then those database schemas, then those attributes and properties that we're storing in our databases could already have the data that this guy needs. It currently does not, because for the feature itself, for the use case, for the functional feature, it didn't need to do that. If my spec says, hey, you know what, you need to keep a record of every login of this user. Boom, that's that. That's all I need to know. That's all the developer needs to know. They create a table with user, login time, login in, login out, period.
Yeah.
But if that developer knew that the data scientist would eventually need some other representation of that same data, that they can compute right off the bat, that they could incorporate in the design, because the functional case, the user story that they're working on, has associated machine learning requirements. So just as right now, and that's kind of like similar to testing, right now whenever you write some user story, whatever, you write tests for it, because you're expecting to satisfy a functional requirement.
Right.
If you could integrate data science into that process, then your user story doesn't just satisfy a functional requirement, it also satisfies a machine learning requirement. And that will influence how you design your data structures. That will influence how you store your data. The closer that design is to what the data scientist will need, the faster your input cycle to your machine learning model is, the faster it will learn, the easier it will be for the data scientist to feed that algorithm with data, and the less complex of your ETL pipeline, the less time it takes to manage the data, and also you reduce the amount of a lot of things that kind of like in data science is kind of cleaning up the data and making sure that you have consistency, because when you're fetching data from multiple systems, some system has a date time in a given format, the other one is different, and so you got to get data from multiple systems. If you have the data scientist involved in the design process from the start, then all of that could go away. See what I'm saying? Yeah. And that's basically the same thing that happened with DevOps between devs and ops, that I think now is an opportunity for the data scientist to now also be removed from the silo and to incorporate all the machine learning and kind of like big data requirements into the constant delivery lifecycle. It doesn't happen afterwards. You don't manipulate data that was built for another purpose. You basically just incorporate data science and machine learning into your product design and development lifecycle. And that will make it a whole lot easier and a whole lot faster for you to eventually, even if you don't have it, implement machine learning prediction and machine learning models, as opposed to having a bunch of disparate systems that have schemas that are completely unfriendly to machine learning, that then make the data scientists have to jump through hoops to get data from all over the place and manipulate it so that they have something that is actionable and that is meaningful to them.
So if you were talking to someone at another company, why would you say, hey, you should really bring your machine learning closer to DevOps because it will do this? Like, what would you say this is? Besides just making everything closer together and faster and more efficient, what does that do? Just provide the benefits of overall machine learning?
Well, it's faster and more efficient. That's the first of all things. You want, the more that you prepare yourself, so it's faster, it's more efficient, and even if you're not doing any machine learning right now, the more closely your data resembles something that a machine learning model can use, the lower the barrier for you to incorporate eventually machine learning into your process. Okay. So you probably don't want to leave that to the end. If you can incorporate, if you can have a sense of what you would want to predict eventually, and you incorporate that mindset, which is basically the data science mindset, into your software design and software architecture, you are getting a strategic advantage to anybody that didn't. Because for anybody that didn't, they're going to have to jump through hoops to get some meaning out of that data. If you incorporate meaning for machine learning into your data from the start, you're going to be faster than them. And you're going to be able to implement machine learning for a lesser cost and with less complexity than anybody who just built their data whatever way they wanted, and then they ask the data scientists to go and make sense of this stuff, right? So it basically, even if you're not doing machine learning, if you eventually want to, and I guarantee you eventually you will have to, you want to make sure that your data science, that your data meaningfulness is represented in your designs from the start, is represented in your architecture from the start. So you don't want data science to be something that happens after the fact, to be something that maybe you're already doing, but is siloed and completely invisible to anybody doing any software development or architecture. You want to put them all together. You want to build it from the scratch with machine learning friendliness from the scratch, just as DevOps started having everybody make products that are easy to deploy. That's why containers are there, right? Because before containers, the developers didn't worry about how this product is going to be deployed. So it was very complicated and cumbersome for operations people to deploy something because it was running in this snowflake setup that the developer used when developing the product, handed off to ops, and ops had to go and figure it out how to productionize this, how to get this running into production, how to make it stable. Same thing is happening with data right now. We got containers, we got ease of deployment, but now the one that has the difficulty is a data scientist. Right now we're building something that can be easy to deploy, easy to support, but the poor data scientist is sitting over there, and once we're done with our product, we say, hey, you know what? Now you go figure it out. Same thing that happened with ops before. I'm done with development, you go figure out how to run this data. If we get them involved from the beginning, just as we now have development and operations involved always together, then you save yourself that trouble. You are faster, you're more agile.
Yeah, this really seems like the next phase. Even with QA in the past, there was oftentimes a separate QA department, and the development group would be done with the coding, and they just hand it off. But now it's much more integrated and automated. So what are the major barriers to people just doing this right away?
I think the fact that they don't know. You know what I'm saying? That nobody, this is early on, machine learning is not a new thing. I mean, it's been there forever, but it's finally getting to be a commodity. The cloud has made it a commodity. Right now you can run your machine learning models. You don't even have to write them for the most part. There's kind of like off-the-shelf available models for predicting, identifying, doing all sorts of things. So it was always, and this is kind of like along the lines of another subject that I was talking to Lara about, in terms of machine learning usually being kind of like associated to this edgy startup that is doing experimental stuff, you know what I'm saying? And, I think a lot of enterprises seeing it kind of like as a lab proof of concept, at most. But enterprises have something that startups don't have. And enterprises have something that machine learning really, really likes, which is data. Huge amounts of data and huge amounts of historical data, right? If you have a startup, you have 3 months of data to work with, or you're using some data set that somebody else produced in some academic setting. If you got a Fortune 500, you got maybe 100 years, 50 years, 20 years of maybe historical data living everywhere, and that's basically the problem. First of all, you want to make sure that from this point forward, you don't continue that trend as an enterprise. That from this point forward, before you had SAP, you had Oracle, you had all sorts of things with data all over the place, and now if you want to go into data science, you say, oh shit, now I gotta put together data from all these different places with obscure, abstract names into something that is meaningful to me. And I think that's basically what is the current barrier, right? Like how do I make sense of this data? What do I even need to make sense? What is it that I'm looking to predict?
Yeah, there's a lot of jobs out there for people who know about data warehousing to just pull data from all these different places and clean it up and do something with it.
Right, because, and that's basically what I'm saying, that those people would have a much more actionable task at hand if they didn't have to spend so much time gathering and cleaning data. And the starting point to that is, or the earliest that you could possibly start fixing that, is if your data is stored from the get-go, from its design, from the initial implementation, your version 1.0, already stores data in a way that is meaningful towards
Isn't that hard to do? Because sometimes you don't know what you're looking for exactly. You just kind of look at the data, getting insights.
That's the reason you need a data scientist in there, because the data scientist is the one that is saying, hey, I've been tasked with predicting something. I've been tasked with creating a machine learning model that predicts X, Y, Z. He knows.
Okay. Like, what would be an example of X, Y, Z?
Anything. I want to predict, let's think about a real use case. I want to predict how long it will take me to get from point A to point B. Uber. Or Google Maps with their traffic thing. I want to predict what you will order next. Uber Eats. You know what I'm saying?
Or airlines, where they most efficiently arrange seats and change prices based on how popular flights are. Flights go up on that.
Yeah. Or for example, I want to predict what likelihood do you have of purchasing an airline ticket if you have a window seat available or an aisle seat available, because I know what you have purchased in the past, or I know what your traveling persona, what your profile has a tendency to like. And that allows me to modify my marketing to you, that allows me to modify everything, to cater to that potential desire, to that potential behavior, right? And those are just kind of like focused on one specific area. Like if I want to market to you something that is meaningful to you, or if I want to give you an app that gives you something, that presents to you something that you have a likelihood of purchasing, or I want to be 5% better at predicting traffic so that you will choose Google Maps or Waze, right? But there are many, many other things. I want to predict traffic. I want to predict in terms of kind of like computer utilization, right, or network utilization. I want to predict online behavior. I want to predict profit. I want to predict loss. I want to predict cash flow. I want to predict what do you want to predict? And that's the whole point.
I guess pretty much anything.
Anything, and that's basically what machine learning is all about. What the output of machine learning, very broadly speaking and very generalized and arguable, but the output of machine learning is predictions. The input of machine learning is data meaningful for those predictions. So that's that's the point, right? Maybe you have to start somewhere, right? So maybe you have to start, once you get your data scientist, you will give him something that you want to predict. And that data scientist will find him or herself into one of two possible scenarios. One is, I need to see where the hell I get this data from, and I need to manage that data, clean up that data, transform that data for it to be meaningful to this objective. Or you get that guy with his objective of predicting something involved in the development lifecycle. And you have them sit down with those developers that are defining the schema, that are saying, hey, this is the table and the rows and columns where I'm going to be putting that data. And you get that guy's input. And maybe what they're storing could be directly and immediately usable for that other guy to predict whatever he needs to predict. So one of the better known frameworks for doing deep learning and machine learning is called Tensorflow. Google has a managed Tensorflow service, so that basically you can just deploy your machine learning model without having anything other than a Google account, a Google Cloud account. And they also have two things that are very important. One is what we mentioned many times about the most relevant thing for machine learning to be effective: data. Who the hell has more data than Google? You know what I'm saying? And they have built a whole bunch of kind of off-the-shelf available machine learning models for all sorts of things, for character recognition, speech-to-text, audio recognition, image recognition, all sorts of things. So they've basically commoditized access to all this, after all, predictive features. When you submit an image to Google Cloud machine learning, whatever service they have, what the machine learning model is trying to predict what that image, what that is. It's trying to identify what that is, right? They've brought that as a service. It's a commodity now. Anybody can use it. TensorFlow also. Okay, these are all technologies that they built, and they have a whole bunch of data that I'm thinking, and this is an assumption. I'm not sure, but I'm pretty sure they're using a whole bunch of the data that they have. I mean, Google Images, YouTube, etc., to feed this machine learning model. So all of a sudden you have kind of this massive amount of data supporting a feature that is using machine learning, that is giving you predictability of stuff without you having to have data.
So you have the benefit of pretty much the entire Google Cloud and the machine learning that's happening there.
For your use case. And if you can't use their machine learning model as it is, then you got TensorFlow managed at an quote unquote infinite scale, right? Because you have the Google Cloud. So you can deploy a neural network of basically any size if you have the money to pay for it. And then the Google Cloud has another thing that is also very kind of like meaningful in terms of, and this is not associated to machine learning, but just to the Google Cloud, and it's how they've built their network. If you look at AWS or Azure, you're kind of like always constrained within the context of a region or a zone or something, so you kind of like know exactly, right? If I want to build geographic distribution or geographic availability, I need to use this or that service, and I have to deploy this in the following regions, and I have to put that up myself. The Google Cloud has kind of like an upside-down network. Everything that happens inside the Google Cloud is happening within a really, really, really fast internal network. And a lot of the features and a lot of the services that they have are basically global by design, global by definition. So you don't have to build it globally. You just use the service, and it is global by default. And some other products that they have also, and this is aligned to kind of like machine learning and whatnot, are there to manage mass data in massive scale, which is something that the competitors have versions of, but Google is particularly good at. And again, Google's is coming from a breed of data. What they've done is they've built mechanisms to manage massive amounts of data. And I think all that experience is reflected in what the Google Cloud has to offer. So if you're looking at machine learning and if you're looking at kind of like neural networks or AI or anything that talks in terms of data and big data, Google has an advantage because I don't think anybody's dealing with data and the capacity that they are. And all that experience and engineering is somewhat available to you through the Google Cloud.
So why should someone pick Amazon as opposed to Google? Or Google as opposed to Amazon? Like one or the other? Like what would be a benefit of choosing one over the other, or a scenario?
That's kind of like, that's almost religion. No, but there are. I think you have to look at what it is that you're looking to build in the first place. You know what I'm saying? Because if you look at the basic tier of services of the three main clouds, they're almost impossible to differentiate, right? Like if you look at the VM, at the virtual machine, and the virtual private network, and kind of like your firewalls and your gateways, and kind of like this basic level of feature set, it almost comes down to what your developers are most comfortable with, right? Because it's, for instance, when I say about kind of Google Cloud being global by definition, global by design, those underlying bare bone basic services are not. Like still, if you go and you do a VM, you're deploying that VM in one specific location, and same thing goes for Azure. Same thing goes for AWS. You pick a region, you pick a zone, you deploy your machine. So if you think you'll stay at that level, it's an argument of kind of like the delivery pipeline and development comfort, developers comfort, right? Pricing you could incorporate in your decision making, but pricing is the constantly moving target, and as much as kind of like the price wars between the clouds has slowed down, they're always going to be on each other's tails to drop prices on this basic set of services. Give me just 1 second. So if you stay...
So Google is really what Qwinix is focused on. So is it the global aspect which I take it by global, you mean that it can interface with anything?
No, by global it means that considering how the network was built, if you deploy a service, the users accessing that service are going to be accessing it from a point of presence that is really close to them no matter where in the world they are. And it's going to be really fast because the traffic is not going out into the wild, it's not going out into the internet. So the difference is with AWS, you have your different regions, and then you pick a region and you deploy your solution there. And if you want geographical redundancy, you have to deploy it in a different region and whatever number of regions you want it to be close to your users.
That's AWS.
Okay? That's AWS. Okay. With the Google Cloud, you deploy it in a global LAN, so to speak, assuming you're using one of these, by definition, global services. It is automatically replicated across multiple geographies. And the users will reach that service by interfacing with a point of presence that is close to them, and their access from that point of presence to the service is happening over a really, really, really fast internal global Google network, okay? So that means no matter where your user is, they're going to be using the closest point of access to get to your service.
That's a tremendous advantage.
It is a humongous advantage.
And Google is the only one that
It's the only one that's doing that. Now, there are some caveats as to that advantage being an advantage, okay? There are some concerns, for example, in terms of legalities, right? Where is your data really located at? Because sometimes, and they have solutions for that. Like if Germany only wants their citizens' data to be within Germany and not to leave the jurisdiction. So you have to kind of, that would be perhaps a little bit more complex to accomplish in Google than in AWS, because in AWS I go and pick up my Germany region, if they have one, I don't remember, my Germany region, and I just deploy my things there, and I know exactly where my data is, and I can constrain it to that location. With Google Cloud, that becomes more difficult, but of course the other side of that coin is if you don't have those problems, you have global reach without any effort. So that is one great advantage. And then the other advantages are kind of like when you're using those higher levels of service abstraction, when you're not talking about the VM and the network, when you're talking about this whole other bunch of services, when you're talking about big data, when you're talking about processing massive amounts of data, when you're talking about commodity ML, when you're talking about also kind of like developer friendliness. One of the things, and this is something I read, I'm just relaying or paraphrasing, that if you look at DevOps, Azure and AWS came in from the ops side to satisfy DevOps delivery pipeline.
Mm-hmm.
Google Cloud came from the dev side. So the Azure and AWS kind of like forces people to think in terms of networks and virtual machines and kind of like container clusters and all these separate things. So it basically came in from the ops side and tried to abstract higher level concepts into developer friendly constructs. Google Cloud came in from the other direction. Google Cloud said, hey, you know what? You really don't need to even know what this infrastructure looks like. You don't have to understand how to deploy a globally resilient architecture. You use us, and that is available to you by default. Matter of fact, this is the other way around. If you need to skip the globality, then you have to go into configuration, because now you have to think, okay, I don't want this data leaving Germany. But if you don't care about that, you don't need the whole concept of VPC, of virtual private cloud, and network, and CIDR range, and IP address. That is completely obscure. That is completely abstracted. And you're going into kind of like just consuming a service. You're interfacing with an API, period. And that gives you global distribution, global reach, and access to massive amounts of scale without kind of like the constructs that AWS and Azure put forth.
Suppose I just wanted to go, I only wanted Asian countries, and I wanted to exclude North America, or vice versa. Does Google allow for that?
It depends on the service, and it does for the most part. It depends on the service, and it depends on exactly how you want to do it, but there you have to think about things a little bit more, in kind of like more in comparison to the other clouds, right? Because all the services in AWS and all the services in Azure, you choose where you want to deploy them. With AWS and Azure, it's very, very easy. I just have to say, hey, I need this deployed in this particular region, and that's done. With AWS, if you're using global services, then you have to think about it more, and the strategies and mechanisms for you to kind of limit your presence to a given geography are a bit more complicated. I think the Google Cloud is there for massive scale, for access to kind of like leading edge services in terms of data and machine learning, for a very simplified way for you to deploy your applications, and basically built-in globality.